The main.java file serves as the system's execution environment and the core integration layer. Its primary function is to manage the application state, presenting the user with a comprehensive menu-driven interface to set up the city and report emergencies. Most critically, it encapsulates the complex dispatch logic between the run simulation function. This process requires dynamic synchronization between all three main data structures. It iteratively pulls the highest urgency case from the BST, or our priority queue, consults the graph to execute the shortest path calculation for every available type matching responder, and finally, updates the location of the chosen unit in memory. This demonstrates our ability to not only implement abstract data structures, but also integrate them into a sequential, real-time decision-making system. The BST.java class is our robust solution for emergency prioritization. While a standard binary search tree is used for general sorting, we leverage its structure to implement a highly efficient max priority queue. When an emergency is logged, its urgency level from 1 to 10 is used as the node's key. Our bespoke extract max method utilizes the inherent property of the BST, where the largest element resides on the rightmost path. By repeatedly traversing right, we locate and remove the critical node in O of h time, where the h is the height of the tree. This guarantees that SKRMS consistently adheres to the critical rule of emergency management. Always address the most urgent threat first, ensuring optimal order of resolution.
The graph.java file is the engine of our system's dispatch efficiency. It models the city's road network as a weighted graph, with each city location represented by a node and the roads connecting them represented by weighted edges corresponding to the travel distance in kilometers. The centerpiece of this class is the implementation of Dijkstra's algorithm, which is executed within the get shortest distance function. This algorithm systematically explores the graph from the responding unit's station, guaranteeing that it finds the shortest path to the emergency scene, thereby minimizing response time. This ensures that the unit ultimately selected for dispatch is the most geographically optimal choice, demonstrating our ability to solve a classic operational research problem. The linked list.java file provides the necessary dynamic structure that underpins two other major components. Primarily, it is the mechanism used to construct the adjacency list within the graph class, where each city node contains the likeness of its neighbors and the distance to them. This provides an excellent space-time trade-off compared to a static adjacency matrix, making it memory efficient for sparsely connected cities. Secondly, it is used by the custom map to dynamically collect the full list of all active responder units for the dispatch routine to iterate over. This allows our system to be scalable and flexible, accommodating the easy addition or removal of routes and units without fixed size limitations.
Custom map.java. The custom map.java file is our custom built hash table, essential for managing all responder units. This structure is implemented to ensure instantaneous access, mapping a unit's string ID or the key to its complete responder object or the value. The process involves a custom hash function to determine the initial array's index. When collisions occur, where two different IDs map to the same location, the class uses linear probing to find the next available slot or locate the existing element. This hashing approach provides a big of one average case time complexity for unit lookups, which is absolutely vital for quickly filtering thousands of units during a critical dispatch decision. Node.java. The node class file is the most fundamental building block in our entire system. It defines a simple object class that separates the data container from the structure logic. This class holds a payload data, whether it's emergency object, a responder unit, or a CT connection, and the essential reference pointers. By creating a unified node class, we achieve a modular design and demonstrated an understanding of how complex structures are built from simple reusable components.
The function responsible for building the city's network enforces bidirectional edge insertion to accurately model real-world two-way roads. This is not simply a single call. It involves two distinct insertion operations into the adjacency list, once from the source node to the destination node, and symmetrically, a second time from the destination node back to the source node, ensuring both are recorded with the same distance weight. This redundancy is paramount for two reasons: completeness in the graph structures and accuracy for Dijkstra's algorithm, which requires that any path taken by a responder is correctly represented, guaranteeing the shortest path calculation remains sound regardless of the direction of approach. The entire speed of responder lookup hinges on the custom string hashing function used in custommap.java. This function is the mathematical mechanism that converts the arbitrary string key, or the unit ID, for example, the passig fd, into a constrained valid array indexed. The implementation involves arithmetic manipulation of the key's character values, often using summation and prime multiplication for better distribution, followed by the modulo operation with the array capacity. The goal is to distribute keys uniformly across the array to minimize clusters. A well-designed hash function is essential for achieving the theoretical O of 1 average case time complexity for insertions and retrievals, which is a core performance requirement for real-time system managing large inventories of units.
The systematic organization of incoming emergencies is governed by the recursive PST node insertion algorithm. This function strictly maintains the binary search tree property based on the emergency's urgency tree. Starting at the root, the function performs a logarithmic time comparison. If the new key is greater than the current node's key, the function recursively calls itself on the right child. If it is less, it moves to the left child. This process continues until a null pointer is encountered, defining the exact diff position where the new node is attached. This insertion discipline guarantees that the structure of the BST is always correct, which is a prerequisite for the efficient extract max operation used for prioritization. During the high-stakes dispatch phase, the system executes an essential linear time traversal for type filtering. After the highest priority emergency is extracted, the system must iterate through the complete collection of all available responders. This OLPN linear loop is computationally necessary to perform a direct comparison of the required emergency type against the unit's stored type. This filtering step is a crucial practical optimization because it eliminates non-eligible units. For example, ignoring police units for a fire emergency from being processed by the much more resource-intensive Dijkstra's algorithm, which saves significant processing time in a large-scale simulation environment.
Dynamic list insertion in linked list class lines 35 to 42. The foundation for the system's dynamic data handling is the dynamic list insertion provided by the linked list class. Specifically, the implementation utilizes a prepending logic, allowing for the addition of a new element at the head of the list in constant time or big O of 1. This is achieved by creating a new node, setting its next pointer to the current head of the list, and then updating the list head's current reference. This method is critical for building the graph's dynamic adjacent list as it enables rapid updates and modification to city connections without the expensive overhead of reindexing or memory reallocation associated with the static arrays. Recursive tree traversal or in order in BST class lines 120 to 135. A fundamental utility function for any tree-based structure is recursive tree traversal, or in order. This function recursively visits nodes in specific sequences like left, root, right. Although not used in real-time dispatch, its importance is purely diagnostic because the BST is structured by the emergency's urgency key. Executing an in-order traversal guarantees that the output of the entire emergency queue is printed in ascending order of urgency. This allows developers to quickly and visually confirm the fundamental integrity of the BST structure and verify the max priority queue mechanism in maintaining the correct order priorities. The Skirms application utilizes a command line interface, meaning the user experience, or UX, is focused on usability, guidance, and data transparency rather than graphical aesthetics. This design approach was intentional to ensure maximum clarity and robustness.
The system employs a menu-driven interface, which presents the user with explicit sequential options, 1 through 7, at every step. This design fulfills the critical UX goal of guided interaction, preventing user errors by clearly defining available actions, whether setting up the graph, adding responders, or running a simulation. The flow is strictly controlled. For example, the user cannot run a simulation until sufficient setup has occurred, reducing operational mistakes. This adherence to clear, concise menus ensures the system is intuitive and easy to navigate, scoring highly on the usability metric.
The SCRMS application prioritizes data transparency to build trust in its dispatch decisions. The system provides clear status reports via option 5, which allows the user to view the full graph connections and the exact station location of every fire and police unit before any simulation begins. Furthermore, the input process itself uses explicit sequential prompts such as enter source ID, enter desk ID, and enter distance or kilometer to guide the user through the complex data entry, ensuring that the critical network topology is configured accurately without ambiguity.
Simulation transparency in real-time state. The most important aspect of the UI UX design is the feedback provided during the simulation from option 6. When a unit is dispatched, the system provides a detailed dispatch log that explains why the decision was made. This log explicitly states the case's urgency from the priority queue, the selected unit's ID from the custom map, and the calculated shortest route distance from the graph's Dijkstra's algorithm. This level of transparency provides immediate verification of the system's efficiency. Finally, the system demonstrates real-time state management by immediately updating the unit's location to the emergency scene after dispatch, confirming that the data structures remain current and ready for the next call.